Constraints are one of the most important topics which you need to understand when using XRNA. For most constraints, almost all of their functions are shared in common across all constraints. These features include linear translation, flipping around a central axis, rotation around a center point, and scaling around the same center point. Typically, this point is either the center of the clicked-on nucleotide or the midpoint of the base pair between nucleotides with the most extreme nucleotide indices. In other words, as is the case with our example file, many RNA molecules feature an extreme base pair involving a nucleotide near the 5' end of the molecule bound to a nucleotide near the 3' end. Most constraints will select that midpoint as the origin of translation, scaling, and rotation. The direction of the central axis is typically perpendicular to the bounding base pair axis. Two other common constraint features are color editing and font editing. We will now demonstrate these common features, but we won't repeat demonstrations for multiple constraints. This is linear translation. Not every constraint supports linear translation. Some constraints are instead based on circular geometry. These include the RNA single-strand constraint and the RNA cycle constraint. This is rotation about a center point. This is scaling about a center point. This is flipping around a center axis. This is the color editor. You can use it to recolor whole substructures at a time. You can use the color editor in several modes. First, you can use the color wheel mode, which is the most intuitive. You can see the available colors as you make your selection. Alternatively, you can use the RGBA mode or the hexadecimal mode. Both of these are useful for precise selection of colors. They may be confusing to users without software experience, but a quick Google search will help you translate a color's name into a hexadecimal encoding. Next, you can see that we can edit the fonts of a whole substructure at once. Font editing involves the selection of a font family, font style, font weight, and font size. The single nucleotide constraint can only be applied to a nucleotide which is not involved in a base pair. It features the unique ability to change the identity of a selected nucleotide residue. This is what it looks like when a single nucleotide is selected. The single base pair constraint can only be applied to nucleotides which are involved in a base pair. This is what it looks like when a single base pair is selected. The RNA single-strand constraint can only be applied to nucleotides which are contiguous and none of which are involved in a base pair. This constraint features the unique ability to place its nucleotides around a circular arc in clockwise fashion, counterclockwise fashion, or straightened out. This is what it looks like when an RNA single strand is selected. The RNA helix constraint can only be applied to an uninterrupted run of contiguous base pairs. This is what it looks like when an RNA helix is selected. The RNA subdomain constraint can only be applied to nucleotides which are part of a bounding base pair within a single RNA molecule. An RNA subdomain is defined as the set of contiguous nucleotides with indices between the maximum index nucleotide and the minimum index nucleotide, which are bound to one another. None of these nucleotides may be bound to a different RNA molecule. This is what it looks like when an RNA subdomain is selected. The RNA stacked helix constraint can only be applied to nucleotides which are part of a base pair. A stacked helix is defined as a run of helices, which are interrupted by single nucleotides. Each side of the base pair helps to locate the RNA strands, which are intermittently base paired to one another. This is what it looks like when an RNA stacked helix is selected. The RNA cycle constraint can only be applied to single nucleotides, which are part of a base pair loop, forming a cycle. This constraint uses a graph algorithm to detect the minimal cycle which involves the right clicked-on nucleotide. This constraint features the unique ability to resize the cycle along with its constituent substructures. This is what it looks like when an RNA cycle is selected. For the last constraints, we will need a different input file to demonstrate the constraints. Please wait a moment while we pull it up. Please note that this file contains multiple RNA molecules, which are colored differently from one another. The RNA molecule constraint includes all nucleotides included in an RNA molecule. It excludes all other nucleotides. This is what it looks like when an RNA molecule is selected. The RNA complex constraint includes a subset of constituent RNA molecules, which may be base paired to one another. It excludes all other RNA molecules. This is what it looks like when an RNA complex is selected. The single color constraint includes all nucleotides which are identical in color to the right-clicked-on nucleotide. It excludes all other nucleotides. This is what it looks like when a single color is selected. The entire scene constraint includes all nucleotides. This is what it looks like when the entire scene is selected. Thank you for taking the time to learn about XRNA constraints. You can explore our other tutorials to learn more.